رضا بما يصنع. In fact, I have my gratitude for all my professors, Professor Kimura, Professor Nishra, Professor Oma, all these international speakers about the electrodiagnosis, especially the conduction studies and EMG. Also, we are talk about some special techniques such as single fiber EMG and reproduction. We are all know what is the importance to use our objective assessment and evaluative tools in either our profession as a physical therapy and rehabilitation, also in neuro, clinical neurophysiology, also in our medical specialties. We have to use these objective tools to put our proper program, gaining speed and specific and almost a good result of treatment. So again, I have my thanks for all the attendees from Iraq, from Saudi Arabia, from Japan or USA, from Singapore, from India, also in my country Egypt. أنا برحب بحضراتكم وإن شاء الله نبدأ بداية كويسة. I'm now with the first talk with my professor Dr. Zakaria to introduce the first talk.
أنا سعيد جدا بتواجدي في مؤتمر electrodiagnosis, electroneuromyography and neuromuscular processes. إذا ده يعتبر إضافة لمادة العلاج الطبيعي. وهنبدأ إن شاء الله الفيرست سيشن with Dr. Kimura under the title of Physiology of Pulse of Impulse Propagation and Waveform Analysis. Professor Kimura, welcome.
Okay, good morning again. I think I'm going right into the physiology. This is I have today and tomorrow a number of talks and workshops. This is the only basic physiology talk, which is very important, right, to understand what we do for neuroprotection studies. I try to speak slow, but if you don't understand me, as I said earlier, you can raise your hand and we can discuss. This is a relatively small group, and we can make it, as we say in the United States, we can make it interactive. You understand? And it becomes interactive only if you guys talk, right? If I just talk, that's not interactive. Okay. Let's see. I can use. Okay. Now, this is just introductory slides. How does it work? Just to show you that I work in Iowa, University of Iowa. University of Iowa, incidentally, is a very distinguished university. This year, we are the Department of Neurology in the University of Iowa, where I went back in 1962. I went to medical school in Kyoto, right? And I went to the University of Iowa to study neurology. And that Department of Neurology this year celebrated 100 years, which is nothing around here. But in the United States, that's very old. This is the third oldest. Harvard, Columbia, and the University of Iowa. So we are really very proud. It's a very distinguished university, neurology department, right? And that's where I work. All right, so to talk about nerve or muscle physiology, I think you always need to begin with action potential, because that's what we measure, right? Action potential. Now, in order to talk about action potential, we have to talk about how the living tissue is polarized at rest. You can take anything. You can take axon, or you can take nerve fibers, muscle fibers, anything, any living tissue. If you, let's say this is an axon, and if you have an ohm meter, and if you put one side inside the axon, and the other end outside of the axon, you always register, depending on species, minus 70 or minus 90. That is meaning inside the cell is negative. This is at rest, when it's not doing anything. Right? So the first question is, how could it be that inside is negative and the outside is positive? Well, there are a number of ways to explain it, but I think this is the best, easiest way to understand. This is a muscle membrane, right? And this is inside the muscle cell, or maybe axon. This is the membrane, inside and outside. And this has all to do with channels. There are a number of channels: sodium channel, potassium channel, chloride channel. Now, at resting stage, only the potassium or potassium channels are open. Right? That's one condition. And secondly, potassium ion, you have more inside compared to outside. I think it can be shown better in here. See, this potassium ion, you have more inside compared to outside. All right, that's one condition. We talk about concentration gradient, because potassium is more in outside, less in more in inside, less in outside. So your concentration gradient for potassium, because they have more here, less here, it tends to go from outside to inside, from inside to outside, right? Because potassium channels are open. But it can't go forever, because potassium ion is positively charged. So as it moves from inside to outside, it takes positivity with it, making inside more negative. And so it can't go forever, because that negativity then begins to attract potassium ion from outside to inside. So at some point, you have to have equilibrium. And that's when inside is minus 90 millivolt. All right, so concentration gradient pushing potassium from inside to outside, electric polarization, negativity inside, pulling potassium from outside to inside. And that's equilibrium, right? Now, what about sodium channel? Sodium ion, you have more outside compared to inside. But it does not move, because at resting stage, sodium channels are closed. So it doesn't matter how much concentration gradient you have, it doesn't matter, right? But if you open the sodium channel, which you can do by electric shock, and in fact, when you do nerve conduction studies, you give electric shock, right? And you talk about cathodal depolarization. Now, why do you want to depolarize the axon? Well, because when you change the muscle membrane potential, you can open the sodium channel. So in fact, when you're trying to activate the nerve, what you're trying to do is to open the sodium channel. Yeah? And if you do open the sodium channel, then what happens? You have more sodium, which is also positive ion, outside compared to inside. So now these guys come from outside to inside to make inside more positive. And pretty soon that positivity begins to repel positively charged sodium, and the second equilibrium is established. And that switch between potassium membrane to sodium membrane is a generation of action potential. That's what we do, right? Okay, so let's take a look, another look here. What I just told you is this. I just told you that at resting stage, and again, this is membrane, this is intracellular inside, and this is outside. At resting stage, potassium can move, right? Because only potassium channels open. And as it moves, it leaves negativity. And I told you that when inside becomes minus 90, this vector, concentration gradient, and this vector, depending on polarization, equals. Yes? But that's not exactly true. And the scientists found out you can calculate this force. And the scientists found out, well, it's not quite equal, this vector and this vector. That's why they said there must be another factor. And that another factor is a sodium-potassium pump. And that's how they found out sodium-potassium pump exists. Now, what does sodium-potassium pump do? Well, it brings potassium in and sodium up in exchange of sodium. So it is exchanging sodium and potassium. This is energy dependent. And when it becomes activated, it takes potassium in and sodium out. And if you add this vector and this vector, which is pulling potassium from outside to inside, it does in fact equal to this concentration gradient. So potassium ion is in fact in equilibrium if you consider sodium-potassium pump. How about sodium channel? I told you that sodium, despite concentration gradient, does not move because channels are closed. And that's not exactly closed either, correct either, because there is so-called persistent sodium channel, and there's a little bit of sodium channel open, and through that little hole, sodium does come in at rest. But it doesn't matter, because that sodium entry is countered by sodium-potassium pump. So sodium, in fact, is in equilibrium at resting stage. You follow me? And this is what we call potassium membrane. But now, if you depolarize the muscle membrane potential and open the sodium channel, then the whole thing is different. This guy now come in, make inside plus 20 millivolt. And that reversal from minus 90 to plus 20 inside the cell is the generation of action potential, right? So this looks like this. Again, this is an axon or muscle fiber. Doesn't really matter, any living tissue. So if you measure the inside, it is polarized. Potassium membrane minus 90 millivolts. So you're sitting here. Now you're going to stimulate the nerve, right? This is the experimental setup. So we are using needle stimulation and stimulate inside the cell. But when you do nerve conduction study, you stimulate the axon from outside the axon. But it doesn't really matter. When you give electric shock, the purpose of giving electric shock is to depolarize. See, this is polarization minus 90. If you give electric shock under the cathode, you depolarize, make the polarization less as you stimulate. All right? And if you depolarize, and if it's not very much, it does die out. Nothing happens. But if you depolarize it to the critical level, or sometimes called threshold, critical to do what? Well, critical to open the sodium channel. Remember, that's the name of the game. Can I open the sodium channel or not? And if you depolarize it, usually 20 millivolts. If you depolarize it by giving electric shock to the critical level or threshold voltage, then here, sodium channel open. And once sodium channel is open, then the sodium coming from outside inside to make inside 20 millivolts. Right? And that's what we call all or none. If you arrive at the critical level, whether you do it slowly or quickly, what happens after that doesn't matter. It always opening the sodium channel and the sodium come in. And if sodium come in, equilibrium is always 20 millivolts plus inside. And so this is what we call all or none, meaning if it doesn't happen, nothing happens. If you arrive at the critical level, always the same thing happens. Yes? Yeah? So all or none relate only to the amplitude, not for the timing of it. If you depolarize using your electric shock very slowly, and if it doesn't arrive at the critical level, of course it dies out. But if it arrives at it, it doesn't matter whether you arrive slowly or quickly. What happens, it doesn't matter. But the latency change, how soon action potential generated changes. Right? And this is the basis of zeta that we can measure with single fiber recording. When you measure single fiber recording, you always get the same spike. But depending on the speed of polarization, the onset of the spike varies, and that variability is the zeta that we measure in single fiber recording. Yeah? Just in passing, I should mention it. Okay, so what then happens after the action potential is generated? Well, the generation action potential, as I told you, depends on the opening of sodium channel. Once sodium channel open, then it has to close. All right, and that closure of sodium channel is called inactivation. In other words, we talk about inactivated sodium channel. Now, there's a little difference between closed sodium channel. Sodium channel is closed here, and once you open the sodium channel, it becomes inactivated, meaning it closes, but it cannot open again for how long? 1 millisecond. And that is the refractory period. So you gotta understand the difference between just closed sodium channel, which you can open if you depolarize to the critical level, but inactivated sodium channel, that means once open and inactivated, then even if you bring the membrane potential to the critical level, that sodium channel is not going to open for you because it is inactivated. And that's 1 millisecond absolute. And therefore, after one action potential is generated, if you want to generate another one within 1 millisecond, you cannot do because the sodium channels are inactivated. 1 millisecond, and that's the absolute refractive period, followed by 3 millisecond relative refractive period, where it is difficult to open, but you can open it, right? So that's another important concept. All right, so these channels that I've been talking about are mostly at the node of Ranvier. Sodium channel is there, potassium channel there, fast and slow potassium. Slow potassium channel tend to be at the node of Ranvier, and fast potassium channel peri-nodal, near the node of Ranvier, So just remember that most of the action is happening here at node of Ranvier. And if you look at the action potential a little bit more carefully, this is what happens. Again, remember this is the potassium membrane minus 90 millivolts, right? And this part, you do it. You stimulate the nerve, right? You stimulate the nerve, depolarize. So inside become from minus 90 to minus 70. And here the sodium channel open. And once sodium channel open, thereafter is an inherent property of the cell. It just goes to 20 millivolts plus inside the cell, inactivated, but it doesn't come down all the way to the baseline. And this hang-up is depending on, see, when this action potential finishes there, the depolarization, because of now when the sodium channel open, inside is plus 20 millivolts, and that plus 20 millivolts is everywhere. So when sodium channels close, it doesn't come all the way down to the baseline, because you have a lot of positivity in here, which tend to come toward the nodal ganglion and make it a little while it's a little more than the baseline here. And this is called negative after potential, which is very confusing, right? And I'm telling you why it is confusing. This is called negative after potential, and in fact, spike itself is called negative spike. If you read the textbook, they talk about negative spike. But it isn't actually a negative spike at all, because it becomes, this is minus 80, and this is plus 20, right? So this actually is a positive spike. Yes? The question is, why do we call it negative spike? And this, in fact, is the positive after potential. Now, why is the term so opposite? Well, that's because when we talk about spike and after potential, we are looking at that activity outside the cell, from outside the cell, not from inside the cell. Remember, when you do EMG, you're looking at the action potential from outside the cell. And so, negative spike, which happens inside the muscle membrane, looks like positive spike outside. I don't know. Do you follow that? It all depends. This is all relative. It all depends where you are. And the term we are using here is the term that you observe from outside the cell and not inside the cell. So it's all relative, right? And so we abandon the use of negative after potential. We are now calling this as a depolarizing after potential, followed by hyperpolar, rather than positive, hyperpolarizing phase of action potential. And this is the hyperexcitable, and this is subnormal. This is, see, this part, once action potential is generated, sodium membrane closes and becomes inactivated, right? So here, you cannot activate the cell again. But once that absolute refractory period finishes, because you are partially depolarized here already, this is hyperexcitable. You can give smaller electric current, and you can open the sodium channel again. So this is hyperexcitable. This is hyperpolarized, and this is subnormal period. And this has a consequence of what you record in EMG study, and which I mentioned to you there. So much for action potential, and I hope this is relatively clear to you. Always, the term you use in EMG is looking at the action potential from outside the cell. Term they use in the experimental study is looking at the action, same thing from inside the cell. And you really have to keep that in mind, right? Okay, so let me just finish this. Okay, so when you look at the cell body, it's like this. There's a cell body, and you have a lot of dendrite. And a lot of people think that when they say something like this, they think this is an axon. It isn't. Axon is very thin. And usually, with this kind of histogram, you don't see axon. You don't. This is another dendrite. An axon is invisible. And so, in order to give you a good perspective, you have to sort of make an illustration. Axon is very, very long. Yeah? Small cell body, you have a very long axon, like in the tibia there. It's close to 2 meters. And so and then you go to, if it's it's a motor action, you go to the muscle. So the next question is, when you activate the cell body, action potential is generated, yeah? But it has to propagate in order to send a signal to the muscle fiber, right? The next question is, how does it propagate, right? So we discussed that. Well, this is another look at the axon here, node of Ranvier, and these are myelin. Myelin is a protective sheath, and we need to understand the difference between myelin and axon. Axon is the nerve fiber, and myelin simply is just a protective sheath, right? Which is very important, though, very important to make conduction, skipping from one node Ranvier to another node Ranvier. Now, how does it happen? Well, this is what happens. All right, so this is the schematic of here's axon and node of Ranvier, right? Now, remember I told you, at resting stage, when you're not doing anything, when this nerve is at rest, inside the axon is minus 90. Remember that? Minus 90 millivolts. And you're going to stimulate this guy, and you have a cathode. You know, when you stimulate, you need two electrodes. One is cathode, and the other is anode. I understand there are some people here who haven't really done the nerve conduction study, right? So I'm going to do some basic talk also. But in order to stimulate, you need two poles. One is called cathode, and the other is called anode. Now, this is also very confusing. Cathode is a negative pole. But the cathode comes from cation, which is a positive ion. But the cathode is a negative pole. Right? Back in Faraday's time, I think somebody made a mistake, calling a negative pole cathode. I think they did that because cathode, negative pole, attracted cation, right? So cathode is negative. In Japan, we don't talk about cathode or anode. We talk about negative pole, positive pole, right? We are simpler people. But so cathode is a negative pole, right? So when you have a cathode here and the anode elsewhere, and you close the switch, what happens under the cathode? Cathode being negative, under the cathode, negative pole, you accumulate negativity outside the cell. You follow? Because it is a negative pole. Accumulating negativity outside the axon is the same thing as accumulating positivity inside. These things are all relative. If you make outside negative, inside become positive. Yes? And making inside more positive is a depolarization. Remember, this is sitting at minus 90,